Okay, we'll look at it. Okay, sorry. So, again, sorry for the late start. Had an emergency come up that I had to deal with. And, yeah. Pretty upset about it. Threw everything out of whack now. The whole week is messed up, but we'll shake it off. Just woosah. And let's actually just continue. So, last we learned about something called an exact equation. What is the form of an exact equation? Well, m of xy. If you leave off the xy, I don't particularly care. Yes, plus n of xy times dy equals 0. What's the condition that makes it exact? Right, particle of n with respect to y is equal to particle of n with respect to x. Whenever that works out, this means there exists some function such that particle of x gives you m, and particle of that with respect to y will give you n, and you have kind of that function hovering over us here, where if you differentiate it with respect to x, you get that. You differentiate it with respect to y, you get that. And ultimately what this ends up meaning is that the solution would look like that function equals a constant by the...
Please don't kill him for using P and Q.
What? I don't care. Okay. So, now, we had some examples, and we just did the method of just integrating the first part with respect to x, integrating the second part with respect to y. Write out the unique functions that show up, sum them all, that gives us our f, and that's our solution. And we had some examples. So let's try to salvage today by running through the rest of the examples and seeing what we can learn from them or apply. So there was a...
We already did it in class.
Oh. That was done. And B was that the e to the x plus x cosine y? Yeah. Right, so we got the x here. Okay, so let's actually do that one. You guys already copied down all the examples, so I'm not going to recopy them. We're just going to do them as they show up. So, who's the n here?
Who's the end of the second one?
The m is the second one. So, try to trick some people. Some people are too smart to fall for it. That is dy dx, which means if you multiply this through by dx, that guy ends up being the guy with dx. Now if I look at this as the n, that is the n, then, and notice that the particle with respect to m of y is equal to e to the x cosine y. And the particle of n with respect to x is e to the x cosine y. That's actually equal to the particle of n with respect to y, so I know it's exact. So that means our solution f is going to be the integral of m with respect to x, which is going to be equal to y e to the x plus sine y plus some constant which could potentially be a function of y, but we don't care at this point. And f is also equal to the integral of n with respect to y, which is going to give us y e to the x plus
X sine y.
x plus some d, and that's it. We don't care about that. There are only two functions that show up. this means our solution is y e to the x plus x sine y is a constant. That's actually going to be the solution. That's implicitly defined. It's actually very hard to solve for y in this situation. So we won't even try. So through C.
But we can't factor out the y.
No.
Oh, yeah.
Yeah, it's inside of a sine. Yeah.
Is it even
It
possible
looks
to
very
factor
unassuming.
Huh?
Right here, it looks very unassuming.
Yeah, you can't factor out the y.
Is it even possible to isolate the y?
Sure, but it's not going to look pretty.
Yeah.
Probably, yeah.
You can take the derivative of this and set it equal to the other one. Let's say you take the derivative of the n function. Set
Okay.
it equal to the original n function, if I would see that one.
Well, that's the other method, which we didn't actually look at.
Yeah, I know that from before.
Is it worth actually even looking at that?
That's all right.
I find this actually easier, but yeah, there's another method, which your book talks about, and some people actually do that. And I guess if you fancy that method, you can do it, but I particularly don't.
That's all right.
This process, the other method works is you kind of cycle through the derivatives. So you would say go through. Either you start with the partial with respect to x, you integrate to get to f, you differentiate to get to y, then you go back to f, or you start with the partial with respect to y, integrate with respect to y to get f, differentiate with respect to x, and go back to the f, while filling in missing parts of f along the way. So how this would actually look, this is probably not a very interesting example to do with it since we didn't really pick up any extra terms here.
The next one might be prettier for that.
Huh?
The next one might be prettier for that kind of thing.
It is, but let me just say it now, because we're here and it was brought up. So what you would do in this situation is you have the y e to the x plus sine of y. So this you think of as the fx, that of course you think of as the fy. And so what you do is you start with the fx. And what we're going to do is we're going to integrate with respect to f and with respect to x, because we want to undo the partial with respect to x. And that would be y e to the x plus x sine y plus some constant which is potentially a function of y, and we don't know what that is. And so what you can do then is differentiate this with respect to y. Why? Well, because it's the guy over here. So then if you differentiate this guy with respect to y, you would get e to the x plus x cosine y, and then you set this equal to, well, the n, right? Because your n is this guy. And so this would be set equal to e to the x plus x cosine y. And now you kind of keep, this is actually plus, don't forget this function here, plus the g prime. So what you now do is realize that this gives you a new equation where you have e to the x plus x cosine y plus g prime of y equals e to the x plus x cosine y. You can subtract e to the x from both sides, that from both sides, and you end up with g prime of y is equal to 0. Well, that means g of y is just a constant. And so now you go back to the f and plug that in. And
Law.
I don't know. I think in practice it's a lot harder for this example, not really, but you get the answer over here. But there's kind of a back and forth here. So you start with fx, then you go to f, then you go to fy, then you go back to f. And if there was a z, you go to fz, then go back to f. You kind of cycle through all the partial derivatives, and you'll get all these guys that are potentially functions of the other two variables, and you just deal with them one at a time.
In 3 dimensions, I know sometimes you can take a convenient z component and start finding a function from there. It's like an easier derivation.
Yeah.
But
We'll actually look at something similar today, but that's usually a trick that you want to apply, especially with partial derivatives. That kind of thing comes in handy a lot. But this is another method. Just cycle through all the derivatives, and each time you integrate with something, you get an arbitrary constant of integration. When you differentiate, you can figure out what that arbitrary constant of integration function would have been, and then you can plug it back in and then differentiate and integrate again until you get to the end of the line and you pick up all the missing pieces. So for a straightforward problem like this, you won't really notice too much difference between the methods, but I think on average, just doing the integration of each part is going to be nicer. It's more straightforward. Unless you suck at integrating, then maybe throwing in a derivative or two to kind of balance out. Okay, sometimes I'm integrating, sometimes I'm differentiating. It depends. Okay, so the next one. Let's see. Is that the e to the x cosine y? That was definitely one of them. Let's actually do that one. And again, I changed the order just to trick you. Of course, that's your m here, that's your n, don't get them mixed up. By our formulation, m is always the guy attached to the dx, that's important. So dx goes with the m, or if you want to be a contrarian like Chris, the dx would go with the t. Oh, come on. And the dy goes with the n. Or if you want to give trouble like some people, not really calling
said you
names
didn't
here, you can call that the key. So, again, you have to do your check. Y would equal to the derivative of that with respect to y. And x, derivative of that with respect to x. So, this means it's exact. So, my function f is going to be the integral of m with respect to x. That's going to be, integrate that with respect to x, e to the x. Just right. E to the x. Sine y plus a constant. And also, f is going to be the integral of n with respect to y. E to the x, sine y. This one is again not very exciting. And so, just one function here, e to the x sine y equals a constant. This one you could actually solve for y, it's not going to be too bad. So your y would be the sine inverse of c over e to the x.
this next one is good times.
Huh?
This next one is good times.
Yeah, you guys like that one? You like that?
You try to do it.
Because eventually, you know, things get a little boring, you have to throw a little spice in there. And we're going to get to D. Okay. y e to the xy cosine 2x minus 2 e to the xy sine 2x plus 2x. Just going to be x here plus x e to the xy cosine 2x minus y equals.
How did they come up with this problem? It's so convenient how it cancels.
So, we're going to do the check. We're going to differentiate this with respect to y, and how do we do this here?
I differentiate that.
Yeah, how do you differentiate this?
Take the cosine 2x out, and then y e to the xy.
Huh? It's the product rule, right? We have two functions of y here, right? That guy's a constant. So, I have to differentiate one, leave the other one, then differentiate the other one, leave the first one. Okay, so differentiate the y, I get e to the xy cosine 2x, plus differentiate the e to the xy with respect to y. What would I get?
The xy.
I get e to the xy times x, right? Because of the chain. So we have cosine 2x. This guy now, differentiated with respect to y, there's only one function of y, so I'm just going to get the minus 2x e to the xy sine 2x. And differentiate that, that goes away. If I look at the next, and differentiate that with respect to x. Now,
This is annoying.
that's a triple product rule, but as we learned from Calc 1, I guess, the product rule just means you write out all the products and everyone gets to be the derivative once, right? So you kind of have that formula in your head. First the f gets to be the derivative, then the g, then the h. So that's what we're going to do. Differentiate the x and leave everyone else. Then plus differentiate the e to the xy, leave everyone else. Then differentiate the cosine, leave everyone else. That's going to give you a minus sign.
That's a really nice formula.
What?
Learn all the tricks.
And we differentiate this. So now we check times 2. Now, of course, that will kill this. This will kill that. That will kill that. They're the same. Equal. Yeah. And the product rule extends naturally for that. There were 4 terms, you just have 4 terms where each one gets to be a derivative once. Yeah. Calc 1. Moving on. You definitely saw that before. Yeah, when I teach calculus, I talk about that.
We didn't take it with you.
So now we are going to so it's exact. Now let's get down to business. F is going to be an integral of m with respect to x. Now, yes, this one is going to be fun. There is going to be
There's an x squared.
where's an x squared? Oh, yeah, we can pick off the low-hanging fruit, right? So, well, there's an x squared, that we know. But one thing there are a couple ways you can do this. You could do integration by parts with e to the xy, and surprisingly, it's not going to be as tough as you think. We could do that with, I'll show you quickly right here. We could do that with,
Can you just identify the middle term?
like I said, you can identify that a product rule happened there.
Yeah.
And kind of figure it out. But if you don't see that, you could have done, when you want to integrate this with respect to x, you can do like a tabular method. So now, if we keep integrating this, what's the integral of cosine 2x?
Negative sine 2x over 2. Negative.
And what is the integral of negative half sine 2x?
Oh, it should be positive.
That's positive.
Oh, yeah.
this is where you get the negative right here, cosine 2x. And now you keep differentiating this guy with respect to x. So don't mess that up. With respect to x, differentiate this.
Y squared e to the xy.
And then differentiate with respect to x again.
Y cubed e to the xy.
You're definitely not following the E8 method.
What?
Well, shouldn't you do trigonometry for exponential?
You can actually alternate those, believe it or not.
I mean, all this seems like way too much work.
Huh? What?
Seems like way too much work.
Yeah, like, what you should notice is that that's the product rule, right?
I don't notice that. Why can't I
but,
notice this? I don't see it.
You can integrate it. What you're going to do is you're going to multiply those two and add it together.
Wait, don't you?
Then you're going to multiply these two and subtract them. Then you're going
Don't you add a
to,
minus sign for every second derivative?
yes. And then you're going to multiply these two and add the integral to these.
Oh, yeah, that's easier to do, right?
So this integral is going to be equal to, well, y over 2 e to the xy cosine 2x sine 2x. And then we're going to do minus y squared, well it's minus a minus, so it's become y squared over 4 e to the xy cosine, that should be cosine 2x. And then I'm going to plus the integral of e to the xy, because I'm multiplying this across, of minus y cubed over 4 e to the xy cosine 2x dx. What you can notice here is that we can actually factor out y squared over 4, and this will be y, and you'll notice that this guy here is your original integral, which is this guy here.
Oh, so now you...
And so now you can bring that guy to the other side and divide that into. Okay, so that's how you would have done it.
What is this other method of, I wasn't seeing the power rule or something? I'm trying to
The
understand.
first two terms in that top expression are just the product rule of e to the xy cosine 2x.
Yes.
So what does that do?
You have to solve the integral.
You don't have to do the integral, because if you notice here, you have an exponential and the cosine and then the exponential and the sine. What you realize is happening is that you differentiated the exponential, left the cosine, and then you left the exponential, differentiated the cosine. So you can see that as a pattern of the product rule right here. So notice if I have here, if I differentiate this with respect to x, I would get y e to the xy times cosine 2x, plus leave the e to the xy, differentiate the cosine, I would get minus 2 sine x, sine 2x. Which gives me the second term.
We figured out the first function analytically from knowing that the product rule happened.
Yeah, so
You
it
can see that.
ends up being that.
Cosine 2x and sine.
Right? So there are a couple ways you could actually do that. So if you didn't see that, you have some work ahead of you. But again, it's not impossible. You'll take an extra 3 minutes, 4 minutes on that problem and try to make up the time somewhere else. Also, if you look at the integral of n with respect to y, here we would get what? Now, with respect to y, that's easier because the only function of y here is the e to the xy, right? So those two, the x and the cosine 2x, we look at it as constants, and I'm simply going to integrate the e to the xy. So we know that the integral of e to the kx is 1 over k e to the kx, where the k is like the x. So that just becomes e to the xy cosine 2x minus y. That's another constant which we actually don't care about. And so ultimately,
Thank you. So, that is a good way to do it.
by the way, tabular integration with all its variations, I teach that to my Calc 1 classes. Like I literally do that at the end of Calc 1. I I've been doing that since the spring. It seems to work out. They get it. They like it. It's really, they're hip to it.
This is good.
So now you're going to have a bunch of students coming in from Jhevon's Cal 1 class again and the rest of the Cal 2. You guys don't know integration by parts? What have you guys been doing? They're like, where am I? Okay. So now, the solution is going to be e to the xy cosine 2x plus x squared minus 3y equals a constant. Taught Calc 1 in the spring, we made it all the way up to improper integrals. After I taught them this. The students are motivated enough, you can do a lot with it. You can do a lot.
What about us?
No, jury's still out, we'll see. We haven't really done anything
What time is your
super awesome yet. We're still in first order of differential equations. We'll start to see later what I can do with you guys. There was one more, right?
No, I think that's it.
There's an E. So this one, again, we can multiply both sides by dx and we get that, so that's not a good thing. Okay. So we go through and we end up with, okay, find my versus next. And you're going to have derivative of this with respect to y is 1. Derivative of that n with respect to x. 2. Okay.
I just stuck a 2 in front of the y. And then it was
You can't do that. It's like maybe Jhevon forgot something. He's gonna tell us next class that he made a typo and he meant to put a 2 in front of the y. Yeah, so did I make a mistake?
Multiply everything by y.
Multiply everything by y. That's a strange coincidence. Set mu equals y. Now mu is the variable that we usually use for an integrating factor. And so you might wonder, what's Jhevon up to here?
Oh,
Multiply through by y. What are we going to get? Well, you're going to get y squared dx plus 2xy minus y squared e to the y. And, okay, now, you multiply through by that thing, and if I find I get 2y. And if I get next, I get suddenly it's exact. Oh, what is going on here? Okay. So, people be doubting me. Like, did Jhevon make a typo? You should have put a 2 there. What's wrong with it? No. See, you gotta get back at all these haters, son. Alright? It was an exact equation. You just had to finesse it a little bit. Now, what we can do, yes, integrate the n with respect to the x, and that is going to be xy squared, plus some constant that we don't really care about. F is n with respect to y, and we're going to get xy squared plus. How do we integrate that with respect to the y? We'll go and do our same thing. y to 0, e to the y, e to the y, e to the y. We are going to add this, subtract this, add this, and so we're going to have y squared e to the y minus 2y e to the y plus 2 e to the y plus some constant I don't care about.
Aren't those all being
The negative here. Oh, you mean from
Isn't
the,
that whole integral on the?
that whole integral is that?
Everything's flipped. Wait.
The negative from here, the minus in front of the y squared.
Oh.
So we actually computed that.
Okay.
So everything is negative here.
Just a quick question.
Yes.
For that method of integration,
Yes.
besides this step you cannot do it because there's a zero, but you just, what do you do the last step? You integrate something? You said before.
Yes, normally, on the last step, theoretically,
You add
there's a
integrations.
multiplication across where you actually integrate on that last step. But
Okay, so
the
multiply-
integral here would be 0,
0 times.
which is just a constant.
Okay. No, but like if it wasn't 0, like let's say it's e to the y times, let's say, I don't know, 2x.
Well, you saw what
Integrate
we would have,
Yeah.
right? We can move it to the other side if it's the same, or if it's something that we can integrate by some other technique, we do that. So, yeah, so this means the solution is that's our answer.
How are we supposed to pick up the mu is equal to y? We're supposed to just like.
Yeah, where did that come from? Come on. Let's see.
We're supposed to know it, bro.
I'll tell you where you can, like I didn't just pull this out of a hat, even though I think it looks that way. I'll tell you how you can figure it out, and I will leave you with 2 examples to figure out on your own. And we'll pick up with that on Wednesday.
Next lectures.
It's maintaining proportionality, right? Is that what's happening?
Is it? It's actually a lot more complicated than that. Like, I'm not.
Are you giving one side, you're giving them all the same thing?
So here, suppose we have m dx plus n dy equals 0, and it's not exact. Sometimes we can make it exact. Bend it to our will. So, say mu of xy is an integrating factor. What you can then do is you can multiply through. So mu times n dx plus mu times n dy equals 0. And what do we want? Well, we want, if I take the partial of mu m with respect to y, I want it to equal the partial of mu n with respect to x. Now, how do I actually force that to happen? So just like with the first order linear, we kind of pretend there's this function that if we multiply through, it's going to make everything better. You know, like when you had a bad day, you go home and you tell your mom, it's going to be all right. You're like, okay, you feel all better about it, or I don't know. Sorry to people who didn't have moms or didn't have loving ones or whatever. It'll get better. Life always gets better. Okay. So now what that means is you need, now for in a partial derivative, there's still a product rule. So we are going to have mu times y times m plus mu times big M sub 1. And that we want to be equal to mu sub x times n plus mu times n sub x. Or in other words,
It needs to be the product rule for us to use it.
we need mu. Let's do mu times my minus, say, nx. I'm just bringing everything to one side. These two have mu's in it, so I just factored out the common mu. Plus mu y times m minus mu x times n equals 0. What kind of equation is that? What kind of derivatives are these? Partial derivatives. So what kind of equation is this?
Partial differential.
A partial differential equation. Now, you want to learn about how to solve those? We have a graduate course that teaches you how to solve those, and even then it's still hard. So, yeah, finding the solution to this in general is going to be really hard. So as Chris, Mr. PQ over here mentioned earlier, sometimes you just want to see, can we make some choices to kind of make the scenario work out nicer? Sometimes it might work. Like I said, for differential equations, because we have the existence and uniqueness there, like a huge bodyguard behind us, just we can kind of do what we want sometimes. You just kind of do what you want and see if it works out later. You act first, apologize later. So that's kind of what we're going to do here. So here's something. Suppose we assume mu is a function of y only. Right? So I'm going to make the assumption, this mu, which I assumed was a function of x and y, let's pretend it's only a function of y. There are no x's. What would that result in?
Raising the power of the
Mu x n is 0.
So if I call this 1, if this is just a function of y, what's going to happen is mu x is going to go to 0, right? So the equation I now would have is the following equation. And now, what can actually result from that? Anyone see what we can do here? Nope. Okay. Here's one thing. Let's isolate the mu's.
Yeah.
What would mu y have to look like? Well, I can move this over there. So I'm going to have partial of n with respect to x minus partial of n with respect to y, and then divide by the mu. And then what I'm going to do here is divide by the n. And I have that.
That's the thing you do.
Now this, I'm pretending it's a function of y. It's pretty much like an ordinary derivative as far as I'm concerned. I can differentiate both sides with respect to y. Or integrate both sides with respect to y. So, of course, the usual story is going to play here. Integrate this with respect to y, integrate that with respect to y. And ultimately, you are going to get that your mu is equal to e to the integral of this guy. By the way, we could play a similar game with the x's. So, if we assume mu was a function of x only, we would get that in that very specific situation, mu is going to be the e to the integral of that dx, right? So you can have a very similar breakdown. So ultimately, and there are other situations. Sometimes we assume that mu is a function of x times y if neither of these work out, and you can kind of just state a form that you want the mu to be in, and then you actually do the calculations for that specific form, because figuring this out in general is really hard. Like, really hard. Like, you have a math degree, you walk into this class like you know everything, and you totally are stumped kind of hard. That's what I mean. So then, so to summarize. So let's suppose you have n dx plus n dy equals 0 is not exact. But I'll give you these two cases. These are the only two cases I'd expect you to know. I'm not going to have you worry about the other cases. But let's suppose case 1. You find that m sub y minus n sub x over n is q of x, a function of x only. And you can work out this case. I didn't work it out for you guys, but you can work out that case and actually see that that's what it would be. Then mu equals e to the integral of q is an integrating factor. That makes the ODE exact. And case 2, if n sub x minus m sub y over m equals, say, r of y, a function of y only, then it turns out mu equals e to the integral of r of y dy is actually is an integrating factor. So here are two special cases for equations that are not quite exact, but you can actually make them exact. Looking at the previous example quickly. For, what was it, y dx plus 2x minus y dy. So now, this was not exact, but I would check one of these two guys. Maybe I checked both. Maybe I checked this one first and it didn't work out, so I checked that one. What you would notice here is if I took note, so we already knew that this was not exact. What I can note is if I look at that function, partial of n with respect to x minus partial of n with respect to y over n, what would I actually obtain here? Partial of n with respect to x is going to be what? 2 minus the partial of n with respect to y? 1 divided by n, so that's y. This is just 1 over y, function of y only. So now, that means that mu equals e to the integral of 1 over y is going to be an integrating factor. But what is that? Well, that's e to the element y. That's just y. So that's how I knew, oh, if I multiply through by y, it will fix everything.
If you did case 1, would it not work?
Well, if we tried case 1, and we looked at my minus next over n, what you would have is negative 1 over 2x minus y to the y. So it's not purely a function of one or the other. So that check didn't actually work, but then doing the other one actually works out. So I can do that.
So right there, when you find if both of them, if q of x and r of y had two variables in it, it's not exact at all.
Right, and there are other things you can do, but for this class, if both of these don't work out, it means you should be trying another technique altogether. Right? It was probably linear, but you missed it, or something like that. Or homogeneous and you missed it, or something. So if both of these don't work out, and I think what I would do for a question like this, if I throw something like this on an exam, I'll put a hint to it and say, hey, there's an integrating factor of y only, and I'll leave you to do the rest. I'm not going to say anything else.
Is there a name for functions that have both, that work out both for case 1 and case 2?
there are many cases. There are many more cases. They're all just too complicated for us. Or just not worth the time. I don't want to spend time. So your book explicitly talks about these two cases, and it asks you to derive another case, but I don't see any benefit to it. Once you get the idea from these two, I think it's pretty nice. Try these on for size. Two examples. Try to apply this idea. X squared plus y, x plus x squared y minus x dy. You can check that it's not exact, but I will tell you your mu is a function of x. Make it exact and solve. B. 1 plus x over y minus sine of y prime equals 0. It's not exact, but assume your mu is a function of y only, make it exact, and solve. You would also notice here that this is nonlinear because of sine of y. It's also not separable, right? So it's also not homogeneous. It's nothing that we've seen before. And it's not even exact. It's literally nothing we've seen before. However, doing this check, we actually could make it exact and use that technique. So try those two. We'll go through them on Wednesday and do some other cool techniques before moving on to chapter 3. I do have physics, yes. Good call. So discombobulated today. Hold on. Let me turn this off.